Okay, so as mentioned before, so the greater the surface area you allow for that reaction to occur on, the number of collisions will go up and the rate will naturally go up, right? The number of successful collisions will go up just because you have more collisions happening. So this is just an example, right? If you have like a big chunk of solid, the only spot where the reaction can happen is on the outside surface of that solid. But if you were to grind that up into smaller chunks or maybe a powder, you now can have the reaction occurring at the outside of each of the smaller portions for that particular solid. Okay, so again, this one really typically can only be applied to solid reactants. And lastly, we have a catalyst. So I know that we've talked about catalysts before, right, in grade 11, as well as when we looked at organic chemistry, a lot of reactions required them. So a catalyst is not a reactant and not a product. Okay, so typically it is something that is added to a reaction that will simply cause that reaction to speed up. Okay, it increases the rate of reaction. And actually how it does that is it lowers the amount of energy required for that successful collision. So if you remember, I mentioned that a successful collision requires two things: the collision of the two particles or three particles, however many are coming together, and when they do collide, they need sufficient amount of energy. So the amount of energy that they actually need has a term, has a name. It's called activation energy. Activation energy. Okay. The symbol for activation energy is E with an A underneath, a little subscript A. So let's take a look at these two reactions. Oh, look, it's a potential energy diagram. You're not getting away from them. So you have your reaction coordinate. This is the same thing as saying like reaction progress or time, right? You have your reactants and then your products. So actually looking at this, all right, this is an endothermic reaction because the delta H is a positive, just throwing that out there. But anyways, the black line is showing you the amount of energy needed for the reactants to become products. So this is the activation energy, right? So however much this is, so let's say, I don't know, this is 20 joules, right? So that means for these reactants to become product, 20 joules of energy have to be put in. That's the energy requirement for a successful collision. By putting in a catalyst, you can see the green line now, what the catalyst does is lower the amount of energy needed. So maybe now it only needs 15 joules worth of energy. So what that means is that before the catalyst was present, let's say there was a collision that had 18 joules, right? So before, 18 joules worth of energy would not be successful because it did not meet the 20 joule requirement. But now that we have that amount and it is catalyzed, it's above the requirement. So this case, it would be successful with a catalyst. So you're actually increasing the amount of successful collisions because you've lowered the requirement for it. So this actually, catalyst does not increase the amount of collisions. It increases the amount of success by changing the energy requirement. All right, so that is essentially, there's 5 ways of affecting the rate of a reaction. And keep in mind, we're talking about speeding up reactions, but you can also slow down reactions, right? So for example, if I want to slow a reaction down, I want to have a lower surface area, right? I would not use a catalyst. I would lower the temperature, right? Lower temperatures typically mean you'll have a slower reaction. I'm going to lower the concentration of my reactants, and maybe I'll use something that's less reactive, right? So sometimes we want to speed it up and sometimes we want to slow it down. So just be mindful, it can go either way.